So, welcome back to our discussion on potential flow and specifically looking at flow past objects in potential flow. And what we have done so far is looked at a very classical problem of flow past a circular cylinder. So, this is the configuration that we have. We have a uniform flow past a circular cylinder and using potential flow solution of superposition of uniform flow plus a potential doublet, we computed what was the velocity field and then subsequently used Bernoulli to find the pressure field. And after that, we saw most interestingly that the drag and the lift in this particular problem was 0. There wasn't any drag in this particular problem, and this fact that there was no drag is something that is paradoxical, and that's the name D'Alembert's paradox. Often, I mean, in a jest, often is said that a paradox is something like if you are recognized enough that you find a mistake or if you find a contradiction in your calculation, then you call it as a paradox. So, you can have a paradox after your name if you are become significantly recognized. So, if you have a uniform flow past a circular cylinder, you do not really need to know fluid mechanics to know that you are going to experience resistance. You can plug your hand into a stream of water, you can wave your hand in air, and you will always experience resistance without having any detailed knowledge of what is going on. You will always experience that there is a work that is being done against the fluid and there is some amount of drag that you will always feel. So, where does this paradox start from, or where is the origin of this paradox? But before we delve into this paradox, it is important to actually focus on the other part, which is the lift part. So, to look at the lift part, we will actually look at a superposition which is now going to be a flow past a circular cylinder with circulation. So, we have done flow past a circular cylinder, which was this particular part is what we did, which was done using a uniform flow plus a potential doublet. Now, we are basically going to add circulation. So, circulation which we are thinking of here in potential flow, this is basically a point vortex. So, at this point I have not told you what is the source of this circulation, what leads to this circulation. You have a cylinder, you have a flow that is arriving at the cylinder. What is the origin of this particular circulation? That is not something that I have clarified, and we will discuss this in a little bit more detail after actually working out what this particular combination gives us. Because you should not be thinking of this problem necessarily as a scenario where the cylinder is rotating. Because if you think of this as the cylinder rotating, then you will immediately realize in a flow that is inviscid, where you allow for slip, there is perfect slip of the fluid on the cylinder surface, a solution that you obtain due to uniform flow plus potential doublet is indeed the same solution for a rotating cylinder. So, the solution that we have obtained here in the previous lecture, that was a uniform flow u infinity that was arriving at a cylinder. The boundary condition that we had was u r equal to 0 at r equals a. There was not any boundary condition on u theta, which means that you could have done this problem for a rotating cylinder and you would have obtained the same thing. The fluid does not care about what is a tangential boundary condition. So, when the fluid is perfectly inviscid, there is no way for you to constrain its tangential motion on solid surfaces. You can do this pretty much the same problem if the cylinder were to spin. There would be no change in the boundary condition. So, at this point, we have not really clarified what is the origin of this circulation, what brings about this circulation. So, we will discuss this after we actually see what is the consequence of this circulation on the flow field. So, As I said, we will now consider a potential flow which is u infinity x that we have already done, lambda cosine theta by r, and then I am basically going to add a circulation. Now, the circulation that I am adding, this is just in terms of ease of the final calculation that we will do. We will add a clockwise circulation or a clockwise rotation or a negative circulation in this problem. It just makes the calculation for the convenience of the calculation. So, if you go about calculating your radial and tangential velocity field, so you know what is your UR. UR is dou phi dou r, u theta is 1 by r dou phi dou theta. Now, the radial velocity UR would be this x, we need to realize it is in polar coordinate r cos theta. So, that turns out to be u infinity cosine theta minus lambda cosine theta by r square. The important part being that there is no contribution from the point vortex to the radial velocity. And this is not really a surprise. You know that the velocity field due to a point vortex is purely tangential. So, when you are doing a superposition of velocity field to an existing velocity field, if you add something that is purely tangential, it is not going to alter your radial component. So, this is not something that is remarkable in terms of your conclusion. But what is going to be a little different is your azimuthal component or the tangential component, because now you have added something that has an azimuthal component in the problem. So, you are going to have minus u infinity sine theta from the uniform flow, and then you will have minus lambda sine theta by r square. So, these parts you have already encountered, there is no difference in this particular part, and then you are going to have a part that is minus gamma by 2 pi r. This is a new part right now. Your combination of your uniform flow plus potential doublet obviously is giving you an azimuthal velocity, but you have a new component to your azimuthal velocity which is gamma by 2 pi r. Once again, I am designing the coordinate system where I label my theta measured in the anticlockwise sense. Okay. So, now boundary conditions. What is the boundary condition? Boundary condition is that UR is equal to 0 at r equals a, the surface of the cylinder of radius a. So, UR is equal to 0 at r equals a, and obviously UR goes to 0, or sorry, UR and u theta. So, the total velocity field should go to u infinity x cap as r goes to infinity, and this we have already done previously. You realize the point vortex is not going to have any contribution at infinity. So, finally, the velocity field, if you apply on UR, if you say UR at r equals a is equal to 0, that gives you lambda is equal to u infinity a square. This result does not change from your previous conclusion. The strength of the potential dipole is the same irrespective of the circulation that you have added, because the strength of the potential dipole actually comes about from your no penetration boundary condition on the surface of the cylinder. So, you can think of the potential dipole as basically capturing effects of finiteness of the object. The fact that there is an object of a given size a, that is actually captured by this potential dipole. Okay. So, we have our radial velocity identical to what we had earlier. Sorry, this was cosine theta, and u theta is minus u infinity 1 plus a square by r square sine theta minus gamma by 2 pi r. So, you are free to choose whatever you want for the value of circulation gamma. That's a parameter that is left arbitrary for you in this particular problem. So, this particular problem will satisfy, repeating again, satisfies boundary conditions for any value of gamma. There is no change in your boundary condition, you satisfy it for all cases. So, this then brings about that, so there is obviously a slight mathematical nuance here in terms of the fact that if you say that you have a solution which solves your governing equation for a given boundary condition and there is a non-uniqueness in terms of this gamma. So, this basically boils down to the fact that there is a certain degree of non-uniqueness that you have, because each of us can have different values of circulation and it gives you different answers, but it all will satisfy the same equation and same boundary condition. So, this comes about in terms of the fact that, just to go over this very quickly, you have this circular cylinder in the domain. So, if you consider a circuit anywhere in the fluid, all these circuits can be reduced to a point, right. You consider a circuit C1, the circuit C1 can be squeezed and made into a point. A circuit here C2 can be squeezed and made into a point. But if the circuit were to enclose the cylinder, it will not squeeze and turn into a point. So, this is basically what is known as the domain is multiply connected, and that has a connection to the fact that we are seeing this aspect of non-uniqueness, and it matters a little bit if you are trying to think a little bit more in terms of the nature of the problem you are solving. But we will stick to flow quantities, we will stick to quantities of finding forces and things like that. So, moving away from that, the first thing we want to check is something that we were interested earlier, which is locate the stagnation points. If gamma was 0, then the stagnation points are at r equals a, theta equals 0 comma pi, right. The location where the x axis intersects the cylinder, the surface of the cylinder, are the two stagnation points. And we saw basically in terms of the fact that the pressure values or Cp attains a maxima at those two locations. Now, what if gamma was not 0? So, now you are going to see some differences. So, if gamma was not 0, obviously we go back to the fact that UR should be 0 and U theta should also be 0. Now, when could UR be 0? UR can be 0 when R is equal to A, right. So, when R is equal to A, so I will label this as case A, when R is equal to A, then U theta would be minus U infinity 2 sin theta minus gamma by 2 pi A. Now, we are choosing gamma here to have a particular sign. So, we are saying that this is the circulation is negative. So, here if I just fix the value of, this is basically the strength of the point vortex. So, if I just fix that strength to be gamma to be here, the magnitude to be positive, then I have a relation here which tells me that sin theta is equal to minus gamma by 4 pi A U infinity, right. So, obviously, when gamma is equal to 0, you are going to get sin theta equals to 0. So, 0 and pi are the solutions. Now, what happens when gamma is basically increasing? So, as gamma increases, so gamma basically keeps increasing, and as gamma increases, you can see there is a bound. The bound is basically 4 pi au infinity, right? Because the moment gamma is greater than the denominator, then the value of sin theta exceeds -1, or rather it's the magnitude is larger than 1. So there is no physical solution for any theta the moment gamma exceeds 4 pi a infinity. So the only validity of this is when the circulation is bounded by this value. So when the circulation is bounded by this value, what is happening here is initially you have these 2 points. The flow would arrive, this is for gamma equals to 0. The flow arrives and there are these 2 stagnation points at theta equals to 0 and theta equals to pi. The moment gamma is non-zero, so now your sin theta is a little larger than 0. So let's say gamma is half, so let's choose a value of gamma. So let's consider gamma to be 2 pi au infinity. So the moment gamma is 2 pi a infinity, your sin theta is equal to -half, which means your theta is basically going to be -30 degrees. That means right now there is a stagnation point which will occur here when gamma is 2 pi a infinity. And similarly, there is going to be one more stagnation point which would basically occur on the other side, right, at 8 pi by 6 or 4 pi by 3, you are basically going to get another stagnation point. So there are these 2 stagnation points which will emerge, or rather which the stagnation points from 0 and pi, they are basically going to move towards theta equals pi by 2, minus pi by 2. So gradually, if you keep now increasing, so if instead of this basically 2 pi a infinity, if it keeps increasing as it becomes 3 pi a infinity, it's just going to, the stagnation points are going to go towards theta equals to pi minus pi by 2. So eventually, when gamma is equal to 4 pi a u infinity, the 2 stagnation points are going to fuse and there will be one single stagnation point. So what does the flow look like when the stagnation points have gone to the bottom half, both of them? When the stagnation points have gone to the bottom half, let's consider the case when we have gamma equal to 2 pi a infinity. So in that case, the flow will now go around this particular point and you will have a stagnation streamline which will look like this. So you will have flow going around. So when you have gamma equals 2 pi a infinity, you will have now the flow going around the cylinder, but there will be a distinct asymmetry that is going to develop. So eventually, when you actually consider the case of gamma equals 4 pi a u infinity. So when you have that, there is a single stagnation point that is there in the problem. So in that particular case, the stagnation point is at r equals a and theta, the location is minus pi by 2. So in which case you are going to get a flow which will appear of this kind. Sorry. This is what the flow will look like when gamma is 4 pi a infinity. But then gamma can take any value. Gamma is not restricted by any particular value. We know that the solution is going to be satisfied irrespective of any choice of gamma. So, what happens when we choose a gamma that is larger than 4 pi a u infinity? What would be the scenario? Clearly, there is no solution for the equation sin theta equals to minus gamma by 4 pi a u infinity. And that is because we want the stagnation point to lie on the surface of the cylinder. So, if you go back to your equations, your equation basically was that for a stagnation point, radial velocity and azimuthal velocity both should be 0. The total velocity field should be 0. Doesn't mean that it has to be on the surface of the cylinder. It so turned out in the absence of circulation that the stagnation points are on the surface of the cylinder. But that is not the definition of a stagnation point. A stagnation point is a location where the entire velocity field goes to 0. So, now if you go back to this, you realize that in the equation for ur and u theta to both go to 0, there is a second possibility that instead of r equals a, it is cos theta equals to 0. There is a possibility of cos theta being equal to 0 is also going to give you a stagnation point because your radial velocity is 0. But for it to be a stagnation point, we should also check for u theta to be 0. Would u theta also be 0? So, for u theta to be 0, we would require minus u infinity sin theta 1 plus a square by r square. We are keeping r now as a something that necessarily is not at a, and then we have minus gamma by 2 pi r. So, if I say cosine theta is equal to 0, and basically I can have two possibilities, one being that if it can either be at theta equals to pi by 2 or minus pi by 2, both would give me cosine theta equal to 0, pi by 2 or 3 pi by 2. So, in which case, because I am looking at this scenario, if theta is equal to pi by 2 or theta is equal to minus pi by 2. So, if theta is equal to pi by 2, then sin theta is equal to 1, in which scenario I would get 1 plus a square by r square minus gamma, sorry, plus gamma by 2 pi u infinity times r is equal to 0. If I choose theta equals to minus pi by 2, then I am basically going to get 1 plus a square by r square gamma by 2 pi, sorry, with a minus sign, 2 pi u infinity r is equal to 0. Is that okay? What should it be? If theta is pi by 2, sin theta is 1, so minus u infinity, is that fine? These are the two possibilities, right? Now, if you take your equation, which is 1 plus a square by r square plus gamma by 2 pi u infinity, I will define this as r by a is equal to 0. So, let me call this variable r by a as some new variable. Let us use zeta as r by a. So, I have an equation which is 1 plus zeta square, and gamma by 2 pi u infinity a is a constant which is greater than 1. So, this is plus that constant zeta square k by zeta is equal to 0, which gives me a quadratic equation which is zeta square plus k zeta plus 1 is equal to 0. This is when theta is equal to plus pi by 2. Now, if you solve this equation, zeta, which is equal to r by a, you are going to get minus k plus or minus k square minus 4 by 2, right? And when you do theta equals minus pi by 2, you have 1 plus a square by r square minus gamma a 2 pi u infinity a r is equal to 0, which gives me now an equation which is zeta square minus k zeta plus 1 is equal to 0. So, zeta is equal to r by a, which is now k plus or minus k square minus 4 by 2. So, k is a quantity that is going to be positive. So, I have let me just make sure so this was gamma by 4 pi u infinity, sorry. So, I want it to be okay. So, gamma is basically greater than 2, sorry, k is greater than 2, because I am interested in the scenario where gamma is greater than 4 pi u infinity by a. So, k square minus 4 is going to be positive. So, that basically gives me a real number, but then here I am going to get the roots that I will get. So, this quantity k square minus 4 is going to always be smaller, square root of k square minus 4 will always be smaller than k, correct? Square root of k square minus 4 is always smaller than k, which means all the roots for this case are negative. All the values that I get are negative, whereas when theta equals to minus pi by 2, I basically get the roots to be positive. So, there will be two solutions. R by a is equal to k plus k square minus 4 by 2, and the other solution is k minus k square minus 4 by 2. Now, k you know is something that is larger than 2, that quantity is greater than 2, k is gamma by 2 pi u infinity a, which means this quantity, the first root, is actually greater than a. This number is actually larger than 1, because k is greater than 2, which means k plus some positive number by 2 is going to be greater than 1, and this number is going to be lesser than 1. So, the summary of all of this is that now you actually have for gamma greater than 4 pi a u infinity, there is going to be a stagnation point at theta equals to minus pi by 2, which is away from the circular cylinder. So, it will look like this. So, you will have streamlines which will bend around the circular cylinder, but there are also going to be streamlines which will remain confined close to the circular cylinder. So, because the circulation is so strong that close to the cylinder you will actually see circular streamlines. It is only far away from the circular cylinder will you see open streamlines. So, this is basically the picture that you would get. So, you would have a picture that initially started out from, so we started out from a picture that in absence of circulation you have these open streamlines that go around the circular cylinder. Then we saw that with increasing circulation, the streamlines basically develop a degree of top bottom asymmetry. So, this is for gamma equals 0, this is for gamma less than 4 pi a u infinity, and now you are seeing the case when gamma is greater than 4 pi u infinity. So, these are the scenarios that you will have. So, obviously the flow field is still irrotational. We have added a point vortex. So, the vorticity is actually inside the cylinder. The point vortex that we have added, if you think of it, it is inside the cylinder at r equals 0. So, the region that is outside the circular cylinder is irrotational. The flow field outside the circular cylinder is perfectly irrotational. So, now doing this exercise is to not just get the velocity field, but also find the forces that the cylinder is experiencing. What would be the force that the cylinder would get? Now, in potential flow, there is one interesting thing is because of Bernoulli, that we use Bernoulli's equation to actually find what would be the pressure field, and then we know that to compute the force that the object is going to experience, we will integrate the pressure field over the surface of the object. Now, just because it is only pressure in your calculation of your force, one interesting aspect is, if you think about the combination of Bernoulli and this particular integration and the velocity field, you can start to think in terms of what would be your force before you do a calculation. So, what this says here is that if your flow field, because pressure goes quadratically with your velocity, right. So, when you have a flow field which basically has this left right symmetry, top bottom symmetry, that will get reflected in your pressure, because pressure depends on the magnitude of the velocity. So, if there is a certain symmetry in your velocity field, that symmetry would basically show up in your pressure. If you remember, the corresponding Cp profile that you got had on the surface of the cylinder had a left right symmetry, right. We measured it over theta, it had a left right symmetry, it also has a top bottom symmetry. We did not go all the way from 0 to 2 pi, we only did 0 to pi, but it was 1 minus 4 sine square theta. So, theta negative and theta positive are the same. There is a top bottom symmetry for the pressure coefficient. There was also a left right symmetry. So, when this quantity has symmetry about left and right, which means that theta between minus pi by 2 to pi by 2 and pi by 2 to minus pi by 2, the left half and the right half, if your pressure is the same, the integral will basically be 0. You are integrating a function which has a symmetry that if you switch theta on from left to the right, you will basically get the same value of pressure. So, you will have a 0 answer. Similarly, because pressure has a symmetry about the midplane, which means theta and minus theta gives you the same value of pressure, then you will have 0 vertical force, or the lift force will be 0. This is before you do a calculation. Now, look at the streamline pictures that you have before we do an integration. The streamline pictures that you have for the cases with circulation, they are preserving left right symmetry. All of them have left right symmetry, and that is not surprising. We have added to this a potential vortex or a point vortex, and the point vortex is obviously something that will not break the symmetry from left and right. So there is a left-right symmetry in your velocity field, but there is no top-bottom symmetry. Top-bottom symmetry is gone. So the flow field has left-right symmetry, but there is no top-bottom symmetry. So this is before you do any pressure calculation. So now if your velocity field has left-right symmetry, your pressure field will reflect that left-right symmetry just because you have the Bernoulli relation to work with, right? If your velocity field was left-right symmetric, your pressure field also should be left-right symmetric, which means without doing any calculation, you can immediately conclude in this problem that the drag should also be 0, right? So the fact that you need look at the streamline, and this is specific only to irrotational flow, because in irrotational flow you have this powerful relation of Bernoulli and steady irrotational, by the way, I will come to the unsteady part later. When you are doing this steady irrotational flow, you have this very powerful relation of Bernoulli that gives you pressure explicitly in terms of velocity. If you have a certain symmetry in your velocity field, it immediately transitions to pressure. This is not true for viscous flows. In viscous flows, if you have a certain symmetry in your flow field, that does not mean it will necessarily show up, the same symmetry will show up in your pressure. It will depend on the kind of problems you are doing. But specific to the steady irrotational flow problem, you can see this directly, that any symmetry that is there in the velocity will exactly get reflected in pressure. Which means that if you have a left-right symmetry in your pressure field, then from the expression of force, there would be no force. And now you can ask the next question. If I have lost my top-bottom symmetry in velocity field, I am not going to expect a top-bottom symmetry in your pressure field. So if there is no top-bottom symmetry in my pressure field, that means I am going to experience some kind of a force in the y direction. So let us just quickly do this formally. So P is basically, or rather P on the surface minus P at infinity by rho is basically half u infinity square minus us square. Now us on the surface of the cylinder is a little bit messy right now, because us is not just minus 2 u infinity sin theta, there is an additional part which is gamma by 2 pi a, right. So when you square it, you are going to basically get a square of 2 u infinity sin theta plus gamma by 2 pi a whole square. So there would be 3 terms here. So one would be 4 u infinity square sin square theta. There would be one more term which is gamma square by 4 pi square a square, and then you are going to get an additional term which would be 2 u infinity sin theta gamma by pi a. So your Cp that you have here, right, if you want to write a Cp, that is Ps minus P infinity by half rho u infinity square is going to be 1 minus 4 sin square theta minus gamma square by 4 pi square u infinity square a square minus 2 sin theta gamma by u infinity pi a. So this was the pressure coefficient that you had in the zero circulation problem. This is a constant that comes in from the pure point vortex part. This is not breaking the symmetry, this is just a constant. The symmetry is broken by this term. right? Sin theta doesn't have symmetry, top bottom symmetry, because sin theta will become negative between pi and 2 pi, correct? From 0 to pi, sin theta will be positive, and from pi to 2 pi, sin theta will be negative. So, this term is basically the one that is responsible in breaking symmetry, and this is a point which you need to see here very clearly. Until the part of calculating velocity, everything was a linear calculation. And then you can always say that if I am doing a linear problem, uniform flow with potential doublet has left-right symmetry. It's more important to focus on these than the algebra. So, you have a uniform flow plus potential doublet which has left-right symmetry, top-bottom symmetry, right? Just a point vortex, gamma by 2 pi r, only this particular problem where the potential is gamma theta by 2 pi, only this particular problem. This is what it will look like. If gamma is, we chose with a minus sign, which means this was clockwise, but this is what it looks like. Now, the two velocity fields independently have left-right symmetry and top-bottom symmetry. You don't need to do anything more, you can visually just confirm this point. The combined problem, when you actually compute, is basically breaking this, and the pressure Cp that you have here in the combined problem reflects this asymmetry, because pressure is a quadratic function of your surface velocity, right? The pressure from this problem plus pressure of this particular problem is not the pressure of the combined problem. That is a point I have repeated few times, and it is important to keep this in mind, that the nonlinearity is not gone away, it is there in the problem, the nonlinearity is present. So, your surface pressure is not a linear combination of the two surface pressures, because if it was a linear combination of the two surface pressures, you would have only obtained these two and nothing else. You have computed the pressure for the Rankine vortex in one of the problems, right, which had a, not a Rankine vortex, but a point vortex. You have done this particular problem, that if there is a velocity field that goes as 1 over r, what is the pressure using Bernoulli? So, you would have obtained a pressure which is similar to this. So, these two, so this is a pressure which is from uniform plus doublet, this is a pressure from the vortex, the point vortex. This is the pressure which is actually coming because you are solving a nonlinear problem. These are the problems in isolation, but it is the coupling which gives you the additional new term. And the reason why I am beating about this particular point is, now when you are going to calculate the force over the surface of the cylinder, so it is A d theta, the force per unit length, 0 to 2 pi, you are going to integrate this, and you have already done this exercise, that integrating this gives you 0, right? Integrating any constant will give you 0. So, the only contribution to your force that you are going to get from this particular term. So, the only integration that I care about or should be doing is integral 0 to 2 pi minus half 2 u infinity sin theta gamma by pi a d theta, right. The other ones are not going to contribute in any form whatsoever. The other ones are going to be identically 0. You can go through the algebra etc., but it does not matter, and there is an n here, normal. So, drag per unit length. So, drag per unit length. So, I will take out all the constant terms, minus u infinity gamma, I have a rho here which I have again missed out. So, there is a minus rho u infinity gamma by pi, a and a would cancel out, 2 and 2 would cancel out. So, rho u infinity gamma by pi minus 0 to 2 pi sine theta n d theta. You don't need to do the other integrals. We have already shown that they are 0. The integral contribution from 1 minus 4 sine square theta is 0. The integral contribution from a constant is 0, and here also I have a constant. So, all those would be not giving me any force. So, finally, this is all that I have to do. And n I know if it is drag, then n should be cos theta. If it is lift, then minus rho infinity gamma by pi 0 to 2 pi sin theta d theta. Integral sin theta cos theta d theta from 0 to 2 pi is 0. Integral sin square theta d theta, however, is integral 0 to 2 pi 1 minus cosine 2 theta by 2 d theta, right. Now, integral cosine 2 theta d theta 0 to 2 pi will also be 0. So, I am basically left with half into 2 pi, which is pi. So, with all this, so let me just make sure my pressure expressions are all okay. So, I have a minus sign here, minus P, and then PS has a minus U. So, the surface pressure is minus U surface square. So, then this should actually be a plus. So, minus and minus will basically give me a plus. So, the final result that we have is FL FD by L is 0 and FL by L is rho u infinity gamma by pi, and the integral is pi. So, that is rho u infinity gamma. So, if you have a flow over a cylinder with circulation, there is a lift force. So, this is an important result. So, even though the drag continues to be 0, and we will actually see this in a more formal manner, that is this 0 because this is a circular cylinder? If it is irrotational, and if it was not a circular cylinder but an elliptical cylinder, if it was a square cylinder, if it was a cylinder which looked like the shape of the letter S, does it matter? And what we will see is that steady irrotational flow gives 0 drag. So, you will get drag 0, doesn't matter. It is obviously the calculation can be done exactly when a circular cylinder. For other cases, you can prove that drag is 0 without having to go through a full calculation of velocity field. But the lift depends on the imposed circulation. So, there are few questions which are still unanswered. What is the source of circulation? And obviously showing that the drag basically is 0 provided we are doing steady rotational flow. And the final point from there where we move on to the next section is how do we address the paradox of 0 drag. So, these are things which we will look into in upcoming lectures. Okay. So, with that I will close today's lecture.